Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the Bootstrap, which is a computational technique to estimate standard errors and build confidence intervals. Let's get to it. We're going to talk about the Bootstrap in the context of the estimation of population parameters. So here as an example, we have a large population of people, and these are their heights. Okay, this histogram, the heights of the population of this large population of people. We want to estimate the mean height, which we call the population mean. However, it's not tractable to measure everyone and then average. Instead, what we do is we obtain a random subset of 400 people, shown in this histogram here in gray, and we average their heights to obtain an estimate. This estimate is called the sample mean, because it's just the average of these samples. And in this case, it's actually pretty close to the population mean, okay, which is 175.6. It's important to realize that this guy is fixed, but this estimate is going to change every time we repeat this measurement process. So if we had taken these 400 other people, the estimate would be different. If we had taken these other 400 people, the estimate would also be different. In general, the estimator, the sample mean, is going to have a certain distribution with relation to the population mean. In this case, we can see that things are okay because we're centered at the population mean and tightly concentrated. So we're going to get a good estimate with high probability. But how do we actually see that? Well, because we have repeated this measurement process 10,000 times and looked at the distribution. But of course, in practice, you're never going to do this, because if you could do this, then you would have access to, in this case, 4 million samples. You would just use all of them to get an awesome estimate of the population mean. Instead, we would like to quantify this uncertainty just from 400 samples, which are the available data. In order to do this, what we can do is we can use confidence intervals. A confidence interval is a range of values that contains the population parameter of interest with high probability, usually 95%. Let's remind ourselves about what logic we use to build confidence intervals for the population mean or for every other parameter where the estimator is distributed as a Gaussian. So we know that by the central limit theorem that we can approximate the sample mean as a Gaussian that is centered at the population mean and which has a certain standard error or standard deviation which is related to the population standard deviation and also to the number of measurements. And now the logic is that if it's true that the sample mean follows this Gaussian distribution, then we can easily come up with an interval here such that the sample mean is going to fall there with probability 0.95. And now the key insight is that if we manage to somehow estimate the width of this interval, then in practice, when we only see the sample mean, we of course do not see the population mean, because if we did, we would have we don't need to estimate it anymore. If we know the width of that interval, then we can center it at the sample mean. And basically, if this guy is in here with probability 0.95, that immediately implies that this guy is here with probability 0.95. Okay, and that's the insight behind confidence intervals based on this Gaussian assumption. Of course, the key question here is, how do we estimate this width? It doesn't seem completely obvious. Okay, here are just some examples of confidence intervals for our example, and you can see that they're always centered at the sample mean, and they have slightly different widths because we have to estimate this width also from the data. How do we estimate this width from the data? We need to estimate the standard error, and once we have the standard error with this Gaussian assumption, we're going to know the width that we need so that the population mean is within the confidence interval with probability 0.95. You can take a look at the video on confidence intervals if you don't remember that logic. How do we estimate this standard error? Well, for the sample mean, we have a formula that we have derived theoretically, which tells us that the standard error is equal to the population standard deviation divided by square root of n. Square root of n, where n is the number of measurements. That we know, right? This guy we know the number of measurements. In our example, we're taking 400 measurements. However, we do not know the population standard deviation. But we can actually estimate it from our data. We can replace that population standard deviation by the sample standard deviation And this usually works quite well unless the number of measurements is very small. Now, imagine that you have an estimator for which you're not lucky enough or smart enough to have derived a formula for the standard error that enables you to estimate it from the data. What can you do? How can we estimate the standard error computationally without the need of such formulas? This is what the Bootstrap is going to allow us to do. If we could sample more data, just to inspire this Bootstrap technique, imagine that you could just get fresh samples. Then estimating the standard error is very easy, right? What do? As we did at the beginning. So we have n data points, we compute the sample mean, we get n other data points, compute the sample mean, and so on and so forth. Okay, we do this many, many times, and then we build this distribution of sample means. Now we're very zoomed in, okay, in case you're wondering why before this thing looked very thin at the beginning of the video and now it's looking much wider. It's just that we're zooming in, okay? And now we can see this distribution. We see that it's actually pretty Gaussian, so that's good news. And now we can just estimate the standard error by computing the standard deviation of the distribution. If we have repeated this measurement process enough, we're going to get a good estimate, okay? In this case, we would find that the standard error is equal to 0.343. Of course, we cannot do this in practice because, again, if we could sample over and over and over, then we would actually just use all of the samples to get an awesome estimate of the population mean, okay? We only have n data points. We have these guys, and that's what we have to live with. So now what we can do is something a little bit crazy, which is to just treat these guys as a population and sample from them in order to try to estimate the standard error. And that's what bootstrapping is, treating your available data as a new population from which you resample. That's the bootstrap. So just to make very clear what we're doing here, we have n samples, which is our data. And what we do is we take indices, n indices at random. So each of these guys has the same probability of corresponding to each of the n indices. And we create bootstrap samples by basically sampling these guys according to those indices. So this looks a little bit complicated, more complicated than it should look perhaps, but I wanted to make this mathematically precise. Basically, these guys are obtained by picking, sampling, resampling from our available data. Okay, remember that our available data is just this small n samples. It's the 400 samples, not the general population. Why is this called the bootstrap? Well, this is the strap of a boot. And the idea is that there's this expression where you pull yourself up from your bootstrap. So I looked a little bit into this, and apparently originally it was used to describe like some crazy scheme that would not work, because of course you cannot pull yourself up over a fence or something just pulling from the strap of your own boot. Nowadays it means to do something on your own. You pull yourself from the bootstraps and you do it. The original meaning is kind of nice in the context of statistical estimation because we're sampling from our data. It's not going to be magic. As we will see, there are going to be some important differences between sampling from our own data and sampling from the population, which would be awesome, but unfortunately is impossible. Okay, so the bootstrap standard error. How do we use this bootstrap idea to estimate the standard error? So we have our samples, our n samples. We have our estimator that we're interested in. It could be the sample mean. It could be something else. In fact, we're going to do this for the correlation coefficient a little bit later on. And now we have bootstrap samples. Okay, we can sample from our data by picking elements from our data randomly to create a new data set of n samples. Okay, so now this bootstrap standard error is the standard deviation of the estimator when we compute it from bootstrap samples. Okay. Of course, in order to compute this standard deviation computationally, we're going to have to approximate it, typically using the Monte Carlo method. And this actually will clarify even a bit. I think it will clarify even more what we're actually doing when we're computing the Bootstrap standard error. So what do? We generate batches of Bootstrap samples. These Bootstrap samples are generated by just picking randomly, uniformly, independently and uniformly at random from our dataset of n samples. Okay, we do this for each batch. We pick n samples at random. So in particular, we're going to repeat some of them. Then we compute the parameter estimate corresponding to each batch. From each of these batches, we compute the sample mean or the correlation coefficient or whatever estimator we're interested in. Okay, this gives us an estimate, a value of the estimator for each of the batches. And now we take this guy and we compute its standard deviation, and that's going to be an approximation to the standard deviation of the estimator, but it's computed from the Bootstrap samples, not from the population samples. If it was computed from the population samples, awesome, we would get a very good estimate of the standard error. Here we're estimating it from the Bootstrap samples because we only have n data points. That is what we call the Bootstrap standard error. It's the sample standard deviation of this guy. Notice that we can make k as big as we want depending on our patience. Okay, we can take many batches. It's just going to be a bit computationally expensive. We'll have to have some patience if we want to make sure the Monte Carlo approximation converges adequately. Okay, so let's visualize what this looks like. Here in gray, we see our original samples, and the Bootstrap samples are obtained by resampling. So we're going to observe that the Bootstrap samples in general are going to look similar, but we are resampling. So, they're going to be not exactly the same as the original samples. So we repeat this many times. Every time we compute, in this case, the sample mean of the Bootstrap samples because we're going to apply this first to the sample mean, and then we will take a look at other estimators. So here for our Bootstrap samples, we obtain this sample mean. We take another set of Bootstrap samples for the same fixed set of data. We get a different sample mean. Again, we resample. Again, we get a different sample mean. Now we can take a look at the distribution of sample means obtained from the Bootstrap estimate. Okay, this is obtained just from our data using bootstrapping. Ideally, we would want to approximate the original true density of the sample mean. But of course, again, there's not going to be a completely free lunch here, right? We cannot hope to completely approximate this guy from the Bootstrap samples. For that, in order to approximate that guy, we would have to be able to sample from the true population, and we cannot, okay, because we only have n data points. So what we observe here, where we do have access to the true population, because we're in this controlled situation where we have access to the population, we're just seeing how things work out. The Bootstrap standard error gives us this, the Bootstrap gives us this estimate of the standard error. The true standard error is actually pretty close. So here the Bootstrap works very well. The standard error estimate obtained from the Bootstrap is actually really good. If we had applied the traditional standard error estimate, where essentially what we do is we compute the sample standard deviation of these guys and divide by square root of n, the estimate would also have been quite good. In fact, it's almost identical to the Bootstrap estimate. And this is not a coincidence. For the sample mean, applying Bootstrap is the same as applying our formula where we approximate the population variance. By the way, there's a square root missing here. Our population variance by the standard, the sample variance, okay? Let's try to understand why that is the case. And again, this only holds for the sample mean. And now our samples that we are, the data, the original data, are like a population. So we can apply oral results about sample means and so on to this new population. In particular, we can consider the sample mean obtained from the bootstrapped samples, which is 1 over n times the sum of the bootstrap samples. And now we can ask ourselves, what is the mean of this bootstrap mean? Well, it's the mean of this population, right? Just by linearity of expectation, or if you remember what the mean of the sample mean is. It's just the population mean. In this case, the mean of this population is not the population mean. because these are just data that are sampled, right? It's actually the sample mean of this data. This is why when you saw this picture, and we'll go back to it, you see a shift between the true distribution of the estimator and the bootstrap distribution of the estimator. What about the variance of this bootstrap sample mean? Well, we know from our derivation of the standard error of a sample mean computed from random samples that it's going to be equal to the population variance divided by n. But now the population variance is actually the population variance of these guys. But that is almost the sample variance. It's not exactly the sample variance because here in the sample variance we put n minus 1. But when you correct for that, it's essentially the sample variance divided by n, which is exactly the formula that we have for the standard error computed in this traditional way where we approximate the population variance and divide by n. This is why for the sample mean, the bootstrap standard error and our usual estimate of the standard error are essentially identical. In other words, these guys are shifted, of course, because this guy, so the bootstrap distribution is centered at the mean of the samples that we actually obtained, whereas this other guy is centered at the population mean. So they are shifted, but their standard deviation is actually quite similar. This standard deviation is exactly the population standard deviation divided by square root of n. The bootstrap standard deviation is approximately the sample standard deviation divided by square root of n. So when the sample standard deviation is actually close to the population standard deviation, the bootstrap is going to give you a good estimate of the standard error. Again, let us remember how we actually use this to build confidence intervals. Well, basically, if we have the standard error, we can estimate this width and then shift it to obtain confidence intervals for the sample mean. And we can do this based on the bootstrap standard error. Remember that for any Gaussian with mean mu and variance sigma squared, we can actually find this constant, which we need to multiply with the standard deviation of the Gaussian in order to find exactly the interval that contains 0.95 probability. It's related to the CDF of a standard Gaussian with zero mean and unit standard deviation. If you don't remember these details, you can go take a look at the video on confidence intervals. But the point is that if you know the standard deviation of the Gaussian, in the case of an estimator, that would be the standard error, then you can build the confidence intervals in this way. In particular, if you want the probability to be 0.95, then that constant is just 1.96. Okay? So now we can apply this to build confidence intervals based on the bootstrap. What do? We take our samples, we have the estimator of interest, we compute the bootstrap standard error by taking a lot of bootstrap samples computing the corresponding estimator values and then the standard deviation of those estimator values. And then we just build a confidence interval hoping that the distribution of the estimator is actually Gaussian. And we'll get back to that point. Okay, so here we plug in our estimate for the standard error in our formula for the confidence interval of a Gaussian estimator. In particular, if we're interested in a 0.95 confidence interval, then the constant is 1.96, and we get our estimate of a bootstrap Gaussian confidence interval with alpha equal to 0.05 in this case. Okay, so then let's apply this to an estimator where we don't have a formula for the standard error. In this case, the correlation coefficient. So we would like to estimate the population correlation coefficient of foot length and height in this population, but we cannot measure everyone's foot and everyone's feet and everyone's height. So instead we have to rely, this is the population correlation coefficient that we want to estimate. Instead we have to rely on just 100 samples. So this gives us this estimate of the correlation coefficient. And we want to know how uncertain we are about it due to this sampling process, where if we obtained 100 other samples, we would see another estimate for the correlation coefficient. So we want confidence intervals, a confidence interval around this value. How do we obtain it? Well, the problem we run into is that we don't have an estimate for the standard error. So how do we build a confidence interval without that estimate? Here I'm showing you that the distribution of the estimator is actually approximately Gaussian. Not completely Gaussian, but approximately Gaussian. So if we manage to estimate this standard deviation, this standard error, we are going to be able to compute reasonable confidence intervals based on the Gaussian approximation. This is just a sanity check. So here the true standard error is 0.051. What do? Well, we apply bootstrapping. We sample from our 100 measurements over and over and over and over. In batches of 100, we compute the correlation coefficient of those batches. And now we have a lot of correlation coefficients. We compute the standard deviation of those correlation coefficients, and that gives us an estimate of the standard error of the sample correlation coefficient. In this case, the estimate of the standard error is 0.056. We see again that the bootstrap, this is the distribution of all those sample correlation coefficients obtained from bootstrap samples. So basically just based on these 100 data points. And it's not that different from the original distribution. It's a little bit different. It's shifted, and we know it's going to be shifted. This also occurred in the case of the sample mean. But this estimate of the standard deviation is not that far off from the underlying one. So that's kind of good news. So now we build our Gaussian confidence interval for the correlation coefficient by plugging in the standard error obtained via bootstrapping and the appropriate constant here. The appropriate constant for 0.95 is 1.96. Okay, so have shown you how we can build confidence intervals for an estimator under the assumption that the distribution of the estimator is Gaussian. What you do is you estimate the standard error via bootstrapping, and then you build the corresponding Gaussian confidence interval. Okay, in this case, for this specific example, these 100 samples that I showed you, this is the confidence interval that we end up with. And it's a good thing that we have it, because we realize that there is quite a bit of uncertainty. It goes from 0.617 to 0.837. Remember that correlation coefficients are always between 0 and 1. So here the confidence interval is pretty large. But still, it clearly indicates that there's positive correlation for sure, right? Like there's no way the correlation would be negative. Here are some confidence intervals that we built in this way, because remember, in our control scenario, we do have the underlying population, and they're all inside except this guy. Okay? If we do this for many 10,000 different samples with N100, we see that the confidence intervals contain the true population correlation coefficient 93.7% of the time, which is great, because the probability that we want is 95%, and as we have seen, the Gaussian approximation is not exact, right? So this is actually pretty good. We have completely bypassed the need for deriving a formula for the standard error of the sample correlation coefficient. Just if we approximate it via bootstrapping, we managed to obtain a good enough standard error to build reasonable confidence intervals. All right, so what have we learned? We have learned the definition of bootstrap, which is basically using the data that you have via resampling to compute, for example, to approximate standard errors more at a high level to try to estimate some property of the underlying population distribution. We have in particular shown how to use this to estimate standard errors, and we have applied those standard errors to build Gaussian confidence intervals. We have shown an example with the correlation coefficient. And that's all I got. Thank you very much.